Hey, this is lesson 2.4 in the AP Calculus curriculum, connecting differentiability and continuity, determining when derivatives do and do not exist. This is from the course and exam description. Our learning objective today is to explain the relationship between differentiability and continuity. And for essential knowledge, we have if a function is differentiable at a point and is continuous at that point, in particular if the point's not in the domain of f and it's not in the domain of f prime. And a continuous function may fail to be differentiable at a point in its domain. So we're going to look at this relationship between continuity and differentiability. When's it differentiable? And then we're going to do some examples. So if you're told that f is differentiable, let's think about what that means. If we have a function f of x and it's differentiable on its domain, and that means at any point on the function there is a tangent line that can be drawn, because remember the derivative is the slope of the tangent line of the curve. That's that's what the derivative is. It's the instantaneous rate of change in the function f of x. So if you had a function that was not continuous, let's talk about the different kinds of discontinuities we had. We had jump discontinuities, we had discontinuities due to a vertical asymptote, or we had removable discontinuities. So let's make some examples of each one. If we had discontinuities due to a vertical asymptote, where if this is the value x equals a, let's see, we had jump discontinuities. And then we had a removable discontinuity. At any of these, there's no way that one unique tangent line could exist. In this case, where the point is, we could draw an infinite number of lines that intersected that one single point on the function. So even though the function is defined at that x value, there's no unique tangent line to define the derivative. For this, for vertical asymptote, there's no y value, there's no function value at the x value a, so there's no way that it could be differentiable at a, because there's no place we could draw the tangent line. And on this one, if we could fill in that one point, remember we call it a removable discontinuity, we could draw the tangent line, but remember the tangent line has to intersect the curve in a single point. So in that case, we would be saying that the tangent line would intersect at a point that doesn't exist. So there's no way you can have a function differentiable at a point where it's discontinuous. So differentiability implies continuity. If you're told that f of x is differentiable, then that implies you can infer f of x is continuous. You might be told f of x is differentiable at a single point, or you might be told that f of x is differentiable on its domain. A lot of times you'll see it says f of x is a differentiable function. That means on its entire domain it's differentiable, and this derivative exists. If it says that f of x is twice differentiable, it means that not only it's the function derivative exists, but the derivative of the derivative exists at every point on the domain. But that does not imply, continuity does not imply differentiability. Let's talk about why that is. Let's recall the limit definition of the derivative. F prime of x is equal to the limit as h goes to 0 of f of x plus h minus f of x over h. And if we want differentiability at a point, we say f prime of a exists is equal to the limit as x goes to a of f of x, whoops, it's f of x, minus f of a over x minus a. For the derivative to exist at a point, this limit must exist. Remember how we defined limits before. If we say a limit exists at a, if the limit exists at a, then that means the limit as x approaches a from the left of f of x minus f of a, that's f of a, over x minus a has to equal the limit as x approaches a from the right of f of x minus f of a over x minus a. If we look at a function, let's look at the absolute value of x. This function is continuous on its domain. No matter what x value you plug in, you can find the absolute value of real numbers. But f prime of 0 does not exist. And that's because the limit as x approaches f, let's define f of x as a piecewise function. And we can say that this is equal to x for x greater than or equal to 0, and the opposite of x for x less than 0. And so if we look for the limit as x approaches 0 of f of x minus f of 0 over x minus 0, then we see, let's do the left first, okay? If we're coming from the left, then that's this part of the function when x is less than 0. So that means that this is going to be the limit as x goes to 0 from the left of negative x minus 0, which is negative x, over x minus 0, which is x. And that limit is, of course, negative 1. Let's do the limit of it as x approaches 0 from the right. Thought I had erasure there. As x approaches 0 from the right, we have to use the other part of the function. And so we get f of x minus f of 0 over x minus 0 equals the limit as x approaches 0 from the right of x over x, which is, of course, 1. And since the limit from the left does not equal the limit from the right, then f prime at 0 does not exist. This boils down to, and what this results in, is anytime you have a function whose tangent lines, as you come up to a point, don't approach the same tangent line, the function is not differentiable there. That can happen when you have a sharp corner. If this is the x value a, then if this was f of x, f prime of a does not exist. If you had a function that's discontinuous at some x value a, even if the limit from the left approaches the limit from the right for the derivative, for the definition of the derivative, the limit definition of the derivative, that's not continuous function, so f prime of a does not exist. If you have a function like f of x equals, let's do the square root of the absolute value of x. This function, if you graphed it, when x was greater than 0, it would just give you a square root of x. When x was less than 0, it would give you the square root of negative x, square root of opposite of x. And so it would be a reflection there across it, a reflection of itself across the y-axis, so it's an even function. It is defined at 0 because we plug in 0 for x, we get 0 for f of x, f of 0. So it's continuous on its domain, but if we look at the limit from the left of f of x minus f of 0 as x approaches 0, then we're looking at the slope of the tangent line. And we can see that that tangent line is going to be negative as we get to 0 because the derivative is going to be negative on the entire part of the domain where x is less than 0. So this is going to be greater than 0, or sorry, less than 0. And we can also see geometrically that the limit as x approaches 0 from the right of f of x minus f of 0 over x minus 0 is going to be greater than 0. Those tangent lines are all positive. And so therefore, the limit, because the limits do not equal each other from the left and right, the limit does not exist. So we can say the limit as x approaches 0 of f of x minus f of 0 over x minus 0 does not exist. So f prime of 0 does not exist. So effectively, f prime of a does not exist if f of a is undefined, means a is not in the domain of the function, or if the graph, if f of a is defined, and the graph of f of a, or of f of x, results in a sharp corner or cusp, that's what leads to the limit from the left and limit from the right of the definition of the derivative, not sharp corner or cusp. If the limit as x approaches a of f of x minus f of a over x minus a does not exist. That's when f prime of a does not exist. As long as we say f prime of a does exist, if the limit as x approaches a from the left of f of x minus f of a over x minus a equals the limit as x approaches a from the right of f of x minus f of a over x minus a. And f is continuous at a. That's when the derivative exists. And so if you're ever asked to justify whether or not or show whether or not the limit exists, this is what you have to do. You have to show the limit definition and explain that it's continuous and the limit from the left and the limit from the right of the limit definition exist. And that's how you do it.